In this video, we're going to talk about classification in Markov chains. We'll start with an example, and this is known as the Ehrenfest model of molecular diffusion. How this works basically is that we have two containers that are the same size, and we can call them containers A and B. And between the two containers, there's a barrier, but things can pass through it. And altogether, there are K molecules in total in those two containers. So it might look something like this: two containers, A and B, and say there's 4 molecules. We're going to define at each step, one randomly chosen molecule is going to hit the barrier in between the containers and transfer to the other. So either from A to B or from B to A. And it's equally likely to be any one of those molecules that hits the barrier. And we'll let xn be the number of molecules in container A after n steps, so after n transfers have taken place. Think about that for a second. We want to model this as a Markov chain. So we want to think about, will this stochastic process, xn, where n equals 0, 1, 2, etc., follow the 3 conditions of a Markov chain? Well, let's think about that and see what we get. If we try to consider the state space, the number of possible molecules that can be in container A at any time is going to be 0, 1, etc. up to k. So it's a discrete state space, so we definitely have that. By the way we've defined it, we also have that xn is a discrete time process because the steps themselves are discrete. And lastly, we'd want to think about whether the Markov property would hold. If we know how many molecules are in container A at a particular time, does that tell us how many there will be at the next step? Well, we'll see if we can find that out. So altogether we have these k plus 1 states, and I want to think about what this matrix P is going to look like. Starting from state 0, where there are no molecules in container A, it's pretty easy to see what will happen. If there are no molecules at all in container A, then the very next thing that happens is one of the molecules from B is going to go into A, and therefore will move the process to state 1. So P00 is 0, P01 is 1, and all the other P0i's is also 0. Same works on the other end. If we had all the molecules in A, so we were in state K, then the only place we could go from there is to state K minus 1, because one of the molecules will leave from container A. But in between, we could go from state I. Well, we can't go to I, because one of the molecules will move for sure, but we could go to I plus 1 or I minus 1. And we just want to think about what is the probability for each of those cases. So here's our situation. We've got, say, 1 molecule in A and 3 in B. The probability of moving from 1 to 2, so from I to I plus 1 in this case, that'll happen if one of the molecules from B is the one that hits the barrier. So the probability of that happening will be the number of molecules in B divided by the total number of molecules, which in general is K minus I, that's how many molecules are in B, divided by K, the total number of molecules. If that happens, if one of the ones in B is the one that hits the barrier, then we'll go from state I to state I plus 1. And similarly in the opposite direction. If we want to go from state I to I minus 1, then one of the molecules in A needs to be the one that hits the barrier and leaves. So that would be a probability of I over K. And you can see, of course, those two probabilities add up to 1, and so we have the rows summing to 1. This is going to hold for I equals 1 all the way up to k minus 1. So we've actually fully defined all of the probabilities for this P matrix. Looking at a specific example where k is equal to 4, we've got 5 states, and our matrix is going to look like this. So each of those values there along the diagonal is 0, and we have the possibilities of moving up or down one of the states. So if you notice, the structure of this matrix is actually kind of similar to the random walk with reflecting barriers at 0 and k. But it's a little bit different because in the random walk, the p's and q's are the same for each row, but here each row has slightly different values of p and q. All right, in this situation, suppose that all the molecules start in container A. I want to find the expected value and the variance of the number of molecules in container A after 4 steps. So give that a little bit of thought, see if you can figure out what information we would need to be able to calculate this, and see if you can give it a try. It might be helpful to have some matrix calculating software handy. Well, what we are told is that we start with all the molecules in container A. In other words, x0 is equal to 4. So if we wanted that vector pi 0, which is where we are at time 0, it would be the vector 0, 0, 0, 0, 1, because we have a 100% chance of being in state 4 and 0% chance of being anywhere else. And we want to calculate the distribution of x4, because if we have that, we'll be able to find the mean and variance of that quantity. So what we need is pi 4. And using the Chapman-Kolmogorov equations, we can find that pi 4 is going to be pi 0 times p to the power of 4. See if you can give that a try. Plug it into your favorite mathematical software. But if you wanted a little bit of a shortcut and you didn't have software handy, because pi 0 is 0,0001, then pi 0 times p to the 4 is just going to be the last row of p to the 4. So that's just a neat little shortcut. And of course, p to the 4, we could take p and multiply it by itself 4 times, or we could just multiply it by itself once to get p squared, and then square that to get, again, the last row of p squared squared will be pi 4. If you have software, you can just use it, but this is just a way to do it quickly if you don't have the software. So p squared, we'll take our matrix and square it, and we'll end up with the following. We end up with a kind of similar looking structure with kind of alternating zeros and non-zero values, and you should check that you can get this as well if you take p and multiply it by p. And then finally, what we want is p squared squared, and we only want the last row of it. So again, if you can do this by hand without too much trouble, we'll get 3 over 32, 0, 24 over 32, 0, and 5 over 32 for our pi 4 vector. So now that we have that, we can find by first principles the expected value of x4, which is the sum over all values of x times the probability. So we'll have 0 times 3 over 32, 1 times 0, etc. as follows, and that will give us an expected value of 2.125. So after 4 steps, on average, 2.125 of the 4 molecules will be in container A. Kind of neat. Here, the numerical value of the process at a particular time actually has a physical meaning. So it does make sense to be able to take the expected value of it because it's measuring a number of molecules. If the state is just categorical, like rain or no rain or win or loss, then it might not make as much sense to take an expected value. But here, where xn represents a number of molecules, then it totally makes sense to take the expected value. For the variance, you can do the same thing. Actually, I want you to try that. See if you can get the correct result, which should be about 0.984. All right, now I want to talk a bit about classification. The structure of the Markov chain is going to have some impact on how it behaves in the short term and in the long term as well. If we think about the examples we looked at during the tutorial, we could have the chain getting stuck in particular states, or we could have the chain only being able to return to a state in an even number of steps, for example. So these factors are going to have an influence on how the chain behaves in the long term. I want to jot down the 3 example chains from tutorial 6, so we have these handy. And these were the transition diagrams. And thinking about the behavior of getting a message from state 1 to state 3. Sometimes it's possible to get a message from one to another, and sometimes it's not. And we define that as being accessible. So we say state J is accessible from state I if there exists some n such that Pij upper n is strictly positive. In other words, that it's possible to get a message from state I to state J. There's a path from I to J, not necessarily direct. So in all 3 examples in the tutorial, we could get a message from state 1 to state 3. But in the second example, it was not possible to get a message from state 3 back to state 1. So we have accessibility, meaning we can get from one state to another, not necessarily directly, just that there exists some path. If we can get both ways, if we can get from 1 to 3 and from 3 back to 1, we would say that those 2 states communicate. The terminology makes a lot of sense here. So if I and J can both be accessible from each other, then we say they communicate. Formally, we'd say there exists M and N such that Pij upper M and Pij upper N are both strictly positive. And again, that just means there's a path from I to J and a path back, but they don't necessarily have to be the same path, and they certainly don't have to be direct. Once we know which states communicate with each other, then we can actually divide the state space into distinct classes, where we define a class as a set or a group of states within a state space that all communicate with each other. And importantly, they do not communicate with any states in other classes. So it's a group of states that communicates solely with the states within that class. And if it so happens that a Markov chain only has one class, in other words, all the states communicate with each other, then we just say that Markov chain is irreducible. It can't be split up into classes, or the entire chain is one class. We can think of an example of that. From the random walk, we have all the set of integers, and that's going to be irreducible. You can always get from anywhere to anywhere. And also, examples 1 and 3 from tutorial 6 had those 5 states being in one class, and so those were irreducible examples. Actually, most of the examples we've looked at in all of our videos so far have been irreducible. We can also further define classes as open or closed. And we say a class is open if the chain can leave the class, but it can't come back once it's left. And on the contrary, we say a class is closed if once it enters the class, it cannot possibly leave. So if we look at example 2 from tutorial 6, we had the following transition diagram, just like that. And we can see that we can split this into 2 classes. States 1, 2, and 5 all communicate with each other. You can get from 1 to 2 and back, going around through 5. You can get from 1 to 5 and back. You can get from 5 to 2 and back. So those are all one class. 3 and 4 are one class because you can get back and forth, but you cannot get back and forth between the top class and the bottom class. We can get from the top class to the bottom class, which means the top class is open, but we cannot leave the class made up of 3 and 4, which means it's closed. So this is an example of a non-irreducible, or I guess reducible Markov chain, where we have multiple classes, and here one of them is open and one is closed. Lastly, I want to talk about periodicity. We say the period of a state I is the positive integer d if and only if it's only possible to return to state I in a multiple of d steps. So for example, if we have the random walk, every state we look at, we can only get back to it in an even number of steps. Think about it. There's no way that you could get back in an odd number of steps to the state you started in. So that means d must be equal to 2, because every even integer is a multiple of 2. Formally, we would say d is the greatest common divisor of all the numbers of steps it can take to get back to the chain. If the period of a state happens to be 1, then we say the state is aperiodic. In other words, it does not have a period. If it's greater than 1, we say the state is periodic. And there's some cool, quick ways to check for aperiodicity. If PII is strictly positive, in other words, the ith diagonal element of that P matrix is strictly positive, then that state I is definitely aperiodic, because we can get directly from I back to I in one step. And so the only number that's a multiple of 1 is 1. So we end up with a period of 1 there. But it doesn't work the other way. If PII is equal to 0, we can't tell right away whether state I is periodic or aperiodic. For an example of that, let's return to example 1 from tutorial 6. Here was what the state diagram looked like. It was just the random walk, I guess, on a circle of size 5. And if we choose any state, we can return to it in 2 steps, 4 steps, but also 5 steps if we go all the way around the circle. 6 steps for sure, but also 7 if we go all the way around the circle and then forward and back 1. So if we think about trying to find the GCD of those numbers, 2, 4, 5, 6, 7, 8, 9, etc., the only number that divides all of them is 1. So d is equal to 1, even though we can't go from a state to a state in a single step. So we've covered lots of new definitions in this video. We had the idea of states being accessible from each other, or communication between states, which is when both are accessible from each other. And that's having a path from one state to the other and a path back. It doesn't have to be direct. We had the idea of classes, and those classes could be open, meaning we can leave the class, or closed, meaning we can't, as well as the idea of an irreducible chain, which is made up of only one class. And finally, we had the definition of a period, where we can only return on a multiple of a certain number of steps, and the idea of aperiodic states, where the period is equal to 1. As you play around with more and more Markov chains, these definitions will become easy to identify, and they'll all have an influence on how the Markov chain behaves in the long run. That's what we'll be talking about in our next video, so see you then.